Hi, in this video, we will solve the problem of converting from a global coordinate system to a local coordinate system. So as you know, the coordinates of the satellite are given in a global system because the satellite sends the geocenter or the Earth's center of mass. That's why their coordinates will be given in an Earth-centered, Earth-fixed system. But we as surveyors carry out our observations on the Earth's surface. That's why we need local coordinates. The transformation is thus a necessity. So for this purpose, we will solve this problem on an example, on an Octave example, by carrying out obtaining the satellites, for example, coordinates in both the polar coordinates and also the ellipsoidal geographical coordinates. So now I have created my Octave script. So XYZ, uppercase to lowercase XYZ. So and by using this, we will transform to a local system. For this purpose, I defined previously a point, and the point coordinates are given by xp. So as you can see here, and I give here the coordinates of a satellite, sort of two satellites, let's say, and we will do for these two cases. So as you see here, xp does not denote to the x component of the satellite. It refers to the vector, so x, y, and z of point P. So these are the x component. For example, this is the x component, y component, and z component. And again, at the satellite side, so the satellite's coordinates are given here, x, y, and as z. So now, first, for making a transformation to a local coordinate system, we need to define the rotation matrix. So let's now write down the rotation matrix of our transformation. So the rotation matrix. So as you can see, the rotation matrix is a function of the latitude and longitude of a point. So now rotation matrix first row will be as minus sine of d b times cosine d L. So here d denotes the angles are given in degree units. So you can also do it in radian units, but in that case, B's and L's must be provided in, of course, in radian units. And the second term here in the first row is sin of d lambda or L, and cosine B times cosine L. So this is the first row. Now proceed to the second row. So it is minus sin D, D times sine D L. The second component will be cosine D L. And the third one will be cosine dB times sine dl. So you see, okay, three components are available in the second row. So this means these are the columns of the rotation matrix. So each, the first component here, the first column, the second row, first column, second row, second column, and second row, third column element. So now the last row now is given as cosine dB 0 and sine dB. So now, so this is our rotation matrix, and the rotation matrix is, let's give the definition here. So it gives the transformation from a local system, so from a local system to a global system. Of course, the vector differences. So let's define these vector differences, for example, dx. So in our case, this will be x satellite's position minus my point position, and this will be given by r times x. So as you can see here, I need the local coordinates, and that's why I need to make or to take the transpose of my rotation matrix in order to obtain the local coordinates given. So, but before proceeding, I need to get the coordinates or the ellipsoidal coordinates or geographical coordinates in ellipsoidal system of my standing point. So my point is given by these three components, the three Cartesian coordinates, and I need to convert these ellipsoidal Cartesian coordinates to the ellipsoidal geographical coordinates, namely the latitude, longitude, and the height, or ellipsoidal height. So for this, I will utilize our previous program generated within this lecture, XYZ to BLH. So as you remember, this program converts to the geographical coordinates, so latitude, longitude, and height. So I copied and pasted before, so the x, y, and z coordinates of my standing point here. And if I give these coordinates, then I will obtain the latitude, longitude, and h. So let's give format long G. So the B is here, L is here, and H is even here. So I am copying simply, then I can make some arrangements in my equation here. So before going to my rotation matrix, providing ellipsoidal geographical coordinates. So these are B, L, and H. So as you see, I'm making some arrangements here. So as you see, the digits are not significant, are insignificant, but I'm okay for the time issue. I'm remain these extra digits there, so that I don't want to erase these digits. So now I have B, L, and H. So although H is not used in this equation, in this rotation matrix, and I can later use H to point ellipsoidal height. So now I need to compute my R rotation matrix. Let's now save and run here. And so these no computation has been carried out already, but I can see now my rotation matrix R. As you can see, this is a 3 by 3 matrix, and we know the property that the inverse of rotation matrix, okay, will be equal to the rotation matrix transpose. So this means the difference between these two matrices will result in a 3 by 3 zero matrix. So this is not the case. So sorry. So we made some mistake here. R transpose times R. So as you can see, so we have some errors. So let's handle this error issue. Let's have a look if we have obtained our rotation matrix correctly or not. So let's now check if this rotation matrix is true or not. So minus sine B cosine dl sine dl. So you have seen here I made the mistake cos dl. So these are missing because d, b and l's, as you see here, are or should be provided in latitude in degree units, sorry. So that's why I put here the d sign, cos d function and sine d function. Sine db, sine dl, cos dl, cos db, sine dl, cos dl. Yes, this is correct. Now let's save and run again. Now again, let's compute R inverse R minus R transpose. As you can see now, so this is the case. So as you see, some terms are different from zero, but this is practically zero in terms of the numerical computation. That's why our matrix R transpose R will result in a unity matrix. You see the diagonal elements 1, 1, and 1. The off diagonal elements will be 0. This we are in the correct path. Now we need to compute the coordinates, local coordinates then. So these are the local coordinates. Local coordinates x, and this will be computed by R transpose times satellite position minus my point position. So let's now calculate this. As you can see, these are the three components in the local coordinate system: x, y, and z. So now I need to compute the satellites polar coordinates. So polar coordinates means that the alpha angle, as you recall from our equation, epsilon angle, and the slant distance, or simply s, let's say. So, and the equation x is given, so let's here define in comment, x is given as times cosine d alpha, for example, and cosine d epsilon, and y, as you recall, is given as times sine of d alpha times cosine d epsilon. And my z component here will be s times sine of epsilon. Now, as you see here, I need to make a conversion between the local coordinates, local Cartesian coordinates, and the polar coordinates given by alpha, epsilon, and s. So for this purpose, I have the local coordinates in Cartesian system, lowercase x, and now I need to derive my polar coordinates, alpha, epsilon, and s. So how will I do that? It is easy. For example, for the determination of alpha angle, I will, as you can see, take the division of y by x. So if I divide y by x, so y function is given here and the x function is given here. So you obtain that the s's will be omitted, cos d will be omitted because they will cancel out, and the sine d divided by cosine d. So this means that this is tangent function. So that's why arctangents x divided by, y divided by x. So, but here I must be aware, because the alpha ranges, alpha angle, as you know, ranges between 0 to alpha angle to 360 degrees. So, or in mathematical terms, this is also this is also valid. So, for example, minus 180 degrees. Okay, alpha angle, and 180 degrees, as you can see. So one of these should be 0, is equal to or greater than, so then, or we can do the other side, the positive one. So by getting this property, we cannot simply use Eitan function. That's why we, as you previously recall from the previous videos, we instead of that use atan 2, and I would like to get the angle in degree units. That's why atan 2d, and division sign will be cancelled and will be removed. Instead of that, I use comma sign. So the alpha angle will thus be obtained in this way. So now, what about epsilon? Epsilon, as you know, so here we can write down the range of the epsilon. It is between minus 90, okay, to epsilon plus 90 degrees. So it will never change. It will never take, 90 degrees. It will never take the absolute values larger than 90 degrees. Okay, epsilon, absolute of epsilon will never be larger than 90 degrees. That's why I can here use a simple Eitan function. So Eitan 2d is unnecessary. So as you see, we always try to use tangents function, because by using tangents, we don't need to make any quarter exploration. So in which quarter my angle will lie, so that there is no need to make any distinction of the quarter. So the program will simply do this for us. So an epsilon, you can see here, will be an atan function, atan d function, of course, and we get the degrees. And for this, I need to divide z by the square root of the x square plus y square. So you see here, if I take the x square plus y square and take the square root of that, I get here s times cos d epsilon. And if I divide z by this norm of the x and y components, then I get the epsilon angle. So atan d will be z divided by s squared t x square plus y square. Now the h, or the ellipsoidal height here, or the s distance, sorry, it is the slant distance, will be the norm of the local coordinate. So the x is a 3×1 vector. If I take the norm, then I get the slant distance of this point. Sorry, from the point P to the satellite S, for example. Now let's run it, and so we have some errors. 29. Sorry. So the point here is that I defined my x coordinates, so x vector, as the components of x, y, and z. So, but that's why instead of x, y, I need to write down x2, the second component of my x vector, and this is the first component. Instead of that, I write x3, and this is x1 and x2. So now let's run, and you see here it is alpha is 34 degrees and epsilon is 5.5 degrees, and the distance is 25 million meters. So this is the distance between my standing point P and the satellite. So is this satellite visible from my point P, my standing point P? The answer will be yes, because I look at my epsilon angle. If the epsilon angle is positive, this means that the satellite is over the horizon. So the angles over the horizon will always be positive. So beginning from 0 to 90 degrees, plus 90 degrees. In the zenith direction, the elevation angle will be 90. And if this angle would be minus, then this would mean that this satellite would not be seen from my standing point. So now one check we can carry out here. If I take, as you see, the difference of the satellite's global coordinates and the point's global coordinates, and take the norm, I will obtain the distance, my slant distance. Let's do that. Norm of xs minus x will be equal to the s distance, sorry, xe. So you see here this slant distance and the distance, or the value obtained by getting the norm of the difference vector will be equal to each other. So now let's take another satellite here. Let's take another satellite, but and for example, this satellite here. The coordinates are given by the xs again. So let's see if this satellite can be visible from the standing point or not. So let's do the same calculations. Of course, I only change the coordinates of the satellite, And let's see. As you can see, the alpha angle, okay, alpha angle will 109 degrees, and the epsilon angle will be minus 82 degrees. So this means the satellite is below the horizon. So that's why I cannot see the satellite, and the distance, as you can see, 55 million meters. So this satellite cannot be visible from my point P. So now let's see where these satellites really are. So for example, on the Earth's surface, for example, let's try to plot the footprint of the satellite on a map. So for this purpose, we will use the special package or consisting of the plotting the coastlines of the Earth, and you will be provided a coastline shapefile, and this can be downloaded with your video. So and you can put this shapefile into your working directory. Let's now carry out this map. So let's do for example, let's have a look which packages are installed in the Octave. This is pkg list, and you see here we will use mapping function, and this mapping function is already installed in our program system, but now we need to load this mapping function. For this purpose, pkg load, okay, mapping, so that I can use the functions of this mapping library. So you see, if I again look at the pkg list, so there is an asterisk here. This means that this is already loaded. So now I will use a shape read function here. For example, world map wm is equal to shape read. So as you see here, this is an 10-meter coastline shapefile. So for that, an 10-meter coastline shapefile, and I'm loading this as WM variable here. Okay, good. Then I can show my map, coastline map, shape draw WM, for example, here. You see, sorry, the coastlines of the Earth, of the entire Earth, in a projection. I think this type of projection is a Mercator projection, angle preserving projection. So let's now put our standing point. So for this, we will use map show here, for example, map show, okay, function, and we will draw here the point, our standing point, and this is given by B and L. So I can simply write B and L because it is already, these are already stored here. That I write, sorry, whose, you can see B, L, and L are already in the memory. So that's why I can use these. And map show, so first you need to provide L, and the second will be B, my point, and let's denote this point as with asterisk and red sign. So as you see here, my point is in Turkey around Ankara, and it is shown by red asterisk. So now let's see our satellite, the first case. For this purpose, I need to compute the footprint. Okay, footprint of the satellite. So this means that I need to convert to the BLH system, or the geographical coordinates. So I have already registered here my satellite position for the first satellite, of course, here. For these values refer to the values given here. Let's run, and you will see here B and L is given here. Let's map show again. B is this, and sorry, first L should be provided. L, and then the B. So let's show this satellite with O and black, for example, and you see now a satellite is over here. So you remember the satellites, the first satellite's coordinates was around. So let's see here the So let's compute the polar coordinates of the satellite. So we will see here, so 34 degrees alpha, and epsilon is 5 degrees. So you see in our system it is the alpha angle with the 34 degrees. So from the standing point P. And of course in the sky, so it can be seen that it is higher than 34 degrees, but the satellite's footprint is on the Earth's surface now. Normally the satellite is at a higher location. That's why it is the 34 degrees. So for example, what about our second satellite here? Our second satellite. So let's compute the geographical coordinates for my second satellite. So that's why let's give x, y, and z equal to y is equal to this value, and z will be equal to here. So I can comment out this here. So let's run. So you see again map show. So I will first compute L here, and sorry, and the B latitude value, and this again will be shown, let's say, with a triangle and a black triangle. And we will see where the satellite is here. So you see our standing point is denoted by red asterisk, and the satellite can be seen, the circle, the denoted by circle can be seen. So it is over Japan, for example, and the next satellite cannot be seen, as you can see. It is because not over below the horizon. It is around the location in Chile. So Okay, so now we have seen how to convert from a global coordinate system to a local coordinate system. So we can obtain a satellite's position in a local coordinate in two ways, either by we can get the Cartesian coordinates, three-dimensional Cartesian coordinates, or the polar coordinates, and we have shown how to compute these coordinates.